Okay, so welcome to the afternoon session, and we're pleased to again have Sam, who's going to present, I guess, his concluding lectures on supersymmetric indices.
Yes, okay. Yeah, so what we've seen so far is that there is this object, the width index, and in supersymmetric quantum mechanical systems, it can be computed in two ways. So we can strip the Hilbert space in theory of the systems, it can be computed in two ways. So we can strip the Hilbert space in the theory. In fact, we only have to, because of the invariance of the index of the various co-continuous parameters in the theory, we only have to compute the Hilberts, only have to determine the supersymmetric ground states of the theory in a specific node theory, which computes the exact index. And that's what we've done so far for this fairly, I should say, a large class of supersymmetric Hamiltonians. So then we have explicitly imputed this thing. And we've matched it with a somewhat different, well, maybe completely different computation. And then we as a path integral, just say, summarize the fields by phi, there is some periodic boundary condition on the fields of the exponential Euclidean action, right? But also here, we used a similar type of technique. We used an argument to say that this path integral is also invariant in the various parameters in the theory to argue that we computed in a certain limit, but that limit gives us the exact answer for the full theory because of the dependence. It gives us the exact answer for the full theory because of the dependence. Okay, and so far, and we saw that these two computations agreed with each other, right? But ultimately, both computations essentially reduced to a supersymmetric harmonic oscillator. Sort of the matching was not entirely easy. But I want to stress that in principle, these are very different computations of the same object. And today, we'll first see how in a somewhat more general supersymmetric model, this can actually lead to a surprising equality. So we can do the computation on this side, get some expression for the index that is not that obviously connected to the left-hand side computation. But and this, what it turns out is that this gives rise to what is known in the mathematical literature as index theorems. Which we'll see along the way what we'll get from this equality. Okay, so to get there, we're gonna first introduce nonlinear sigma models. So, symmetric sigma models. Luckily, we've already seen them appear in this morning's lecture. So let me explain how this arises in a mechanical context. So far we have looked at the propagation of a particle mostly on the real line, though we've also briefly discussed the case of a particle moving, a whirlwind moving in Rn. Now we're going to take a particle moving in a general Riemannian manifold, M, manifold of dimension n. Okay. So if we denote by x of a coordinates on this manifold, then we're interested in the world line of a particle, x of p, which is a map from time, its world line, into the manifold. So the picture you should have is that time is the vertical direction here, and the time slice is given by this manifold. Then this particle is just moving around this manifold. Okay. We're going to write an action for this system, and that's what is known as the nonlinear sigma model. Let me fit that. It doesn't require which space. The bosonic one. The bosonic one is given by the following action. It's just the metric on this manifold M there is some function of the coordinates on that value times x dot x dot a x dot okay. So this is essentially also so what we have here is that an ordinary kinetic term, but now there's a prefactor that depends non-linearly on the function x of t. So, okay. So that's where the name non-linear comes from. We've seen these type of models this morning in Mario's lecture, where it was considering some scalar manifold. And the scalar fields, their kinetic terms, if I'm not mistaken, coupled to the metric on the third experiment in exactly this way. Also, if you've seen the string the string theory worldsheet action, that's just a two-dimensional generalization of this, right? Where now we have, instead of a world line, we have a two-dimensional world sheet. The world sheet, scalar fields on the world sheet are interpreted as a target space over these. That's the same here. So this action is supposed to describe the movement of this particle on this manifold. And indeed, if you compute the equation of motion, which is not too tricky, so let's do it in a little bit of detail. So let's vary the action. So delta S x is equal to it's given by the following. So we have first delta acting on the kinetic term, but we should also consider the variation of the metric, because the metric depends on x. And we're varying x. So we also consider that variation, which is 1/2 delta G AB delta XC times x dot A x dot B delta C. Right. Okay, so as usual, you do a partial integration on this term, and factor out delta XC, and you'll find that the equation, and put that equal to 0, and then you'll find that the equation of motion can be written in the following way. It's t squared of XA coming from this term, and then we have zero, where gamma is nothing but the H beta connection associated to the metric. We have the times times okay. Okay. So these Okay? So these last terms come from both this term is the last one, and then the time derivative acting here is the other terms. And this is nothing but the geodesic equation. So we see that indeed the nonlinear sigma model action produces an equation of motion such that this particle is moving around geodesics on the radial. Okay, but this is just the bosonic system. Of course, we are interested in supersymmetric systems. We have include fermions. Just like the previous time, we, in Rn, we include n complex fermions, and their action is given as follows. We have just the connector is about G, star A is that B. Now we also have connectors for fermions given by I, A, G, A, B, psi, dagger, A. Now covariant derivative. Covariant time derivative of psi. Yes, that's. And finally, what is necessary to make this system symmetric is some coupling of the Riemann tensor, which contains the axis, with the fermions. There's a 4 fermion term that couples the bosons to the Riemann. Okay. And the claim is that this is a supersymmetric action with respect to the supersymmetry transformations delta xa. So notice that these transformations in the laterite are very similar to what we've seen previously. In fact, this transformation is identical. The transformations of the fermions are slightly adjusted. So we still have the term that we also had for a previous class of Hamiltonians, so a time derivative of the bosonic fermions. Now there's no potential H included in this action, but we do have this interaction there, and it turns out that this interaction term requires us to add something proportional to the H beta connection, psi to psi c. Okay? And then finally, a very similar looking equation for Okay. So the claim is that this action is invariant over these transformations. They indeed take the form of supersymmetry transformations, bosons and fermions are exchanged. Now, to actually check that, we're not going to do it live. There's in the lecture note by Tom, there's a fairly detailed derivation of this invariance. It's considered by all references that I know that I've used to be a very, very good exercise to check this. So they all encourage the reader to check it. and I'm going to do the same. But yeah, I mean, it's doable. And in Tom's section notes, it's very explicitly done. Okay, so let me also write the associated negative charges without derivation. So the associated negative charges, again, look very similar as what we had before. So we pointed out the differences. So remember that the previous supercharge, of course, didn't have a metric, because our metric was just the flat metric we're working on Rn. And moreover, we just had an additional term here corresponding to H prime, the potential, but now we're working without this potential. So these are indeed very, very similar to what we've seen before. This guy is given side here. Okay. Any questions about this? I'm just throwing formulas at you, so but we'll have to set up some of the formulas to appreciate what is to come. Okay.
Sorry,
Yep.
what's the second term in the action?
The last one, or the second one?
Second term, yeah.
Oh, I didn't define it here. Okay, so it's a covariant derivative of psi. So maybe I should define the covariant derivative. So T of psi A. So it's really the pullback of the covariant derivative from the target space to the line of the particle, and it's given as follows. It's E tau psi A plus, as usual, we've got the Chivita connection, but now there's this additional this term that pulls it back to the world term. So I see. Okay. Yeah. The reason that these fermions have a covariant derivative acting on them is because if we can view them, they're not scalar on the target manifold, but they are some section of a bundle of other target manifold. And so they are particularly dependent on it. So they're sensitive to the curvature of the target space. But I don't want to go into those details. What I do want to do is to now quantize the system. The first one to look at the computation of this side of the index, so the trace formulation of the index for this supersymmetric sigma. Sorry,
Isn't there any impact?
No, because in this case, so yeah, that's a slightly confusing thing, but if the spin connection is necessary for the base space, so the space in which is, so for four-dimensional fermions, they transform as spinners on the, how do you put it, the target of the world volume, the world line world volume. And that's where they are spinners, and then you have to couple them to curvature through the spin connection. In this case, we're talking, this guy is defined on the target space. And in the target space, they just have this tangent space, ordinary vector tangent space in this.
Then the Lorentz group on the line, along the one-dimensional world line is like
So
the Lorentz group on the
yeah,
RT.
yeah. So we never have to worry about spinor representations in quantum mechanics because these are just one dimension. The world line is one dimension. That's okay. So we want to quantize this system. So to do that, you first have to compute the conjugate momenta. So this guy is, as usual, computed by this functional derivative of the action. And okay, I'm not really going to use this, but just let me write it down. So the reason, so this term is the usual term that you know, which is easily seen. There's an additional term in the case of the supersymmetric signal model, which has to do with the fact, which has to do with just to do with the fact that there is precisely this covariant derivative in the fermion term, which couples the time derivative of x also to the fermions. So that's where the second term is. Okay, and similarly, conjugate momenta for the fermions, which you get by varying the action with respect to time dot. This is equal to psi dagger capital P. So that's the common expression, except for the fact that we now have a non-trivial metric here. Okay, and then you put these guys in the usual way. So we say that we promote coordinates and momenta to operators. We promote coordinates and momenta to operators. Now it's important to keep track of the indices, whether they up or down. But in this way, we have this ordinary composition of coordinates and momenta. Similarly, well, we can do the same with the fermions. You get an anti-commutator. So you promote the fermions to operators, gas-mental operators, and get an anti-commutator that works out to be is now proportional to the inverse metric. Okay, and we also have that side A, side B is equal to side vector. Then A and B, this is just equal to 0. Okay, so these commutators now suggest a specific interpretation of how the Hilbert space of this theory is organized. Let's see that. So let's start just with an ordinary ground state. Now we have n fermions. So we can treat these fermionic operators as creation operators. So we can put one of them and put two of them. Two of them. one. So in the simplest case, with one complex fermion, we just had a two-dimensional representation. Now that we have multiple fermions, we have 2 to the power n, 2 to the power n dimensional representation. But there's nothing more, right? Because any extra psi dagger would mean that there are 2 psi daggers of the same pattern, which annihilates this. Okay. Now the idea is to think there's a very natural correspondence between the Hilbert space associated with its model and differential geometry on the target space. So the idea is that we're going to the ground state to just the constant function. But now these the ground states which have an action of psi dagger on them, we're going to associate them to differential forms. So this guy we associate to the basis one form dxa. That's all fine, but why does it work? Well, this is exactly because if you look at this ground state with the action of 2, you see that because it's anti-symmetric, it naturally corresponds to these 2 forms, to the wedge product to 1 forms. Right? So that may seem a little bit, and the last one will correspond to the volume forms. Dxn is 1 to dxn. Count the volume form, can't go to high dimension form. So there seems to be a natural correspondence with these guys. And this goes further. So we can also use that. So far we've interpreted in some sense this commutator. We've also interpreted this anti-commutator in the differential form language. So what does this tell us? Well, it tells us that if we act some psi b, a lower term operator on some psi 1 to psi p acting on 0, you can write this as the anti-commutator of zero, because psi annihilates 0. And then we plug in what the anti-commutator of psi with any single psi dagger here. And what you find is that you get a metric G A1 times psi dagger A2 up to psi dagger AP minus, then we replace this index by A2 and leave out A2, we have A1. And the minus sign alternates, acting on 0. We now translate the differential form language, we see that this lowering operator corresponds to the contraction with a vector field. So contraction meaning that we you just kill one of the axes in the P form that is associated. So okay, so we have some way to understand psi and psi dagger in terms of differential geometry. So now the proposal is that then that the wave function so the proposal is that previously we thought about the wave functions, remember, as this L2. So square integrable functions on our target manifold previously was R, values, of course, would be the complex numbers. Previously, we thought about our Hilbert space in the following. So some wave function and then the extra label determining whether we are working with fermion or a boson. So this was our previous decomposition of the Hilbert space. Now, in this for these n fermions, we can instead now write the Hilbert space in the following way. N, where we interpret this as ordinary functions, which are zero forms on our manifold. But we're going to interpret these guys as one forms all the way up to the vacua acted upon with n fermions and psi layers, which would give us the top forms of this manifold. The idea is that, the idea is that we can understand the Hilbert space as differential form language in this particular way. So an inner product, natural inner product on for differential forms is that if we have alpha and beta both being some influence, right, then we can define an inner product by taking alpha bar complex conjugate wedge star alpha bar complex conjugate wedge star. The star is the Hutch dual. And we get, this is a top form because the Hutch, so this is a P form, and the Hutch dual in the P form is an N minus P form. So this is a top form which we can integrate over the whole manifold, and this gives an inner product. Particularly, our original inner product for, let's say, just wave functions in this space becomes as follows. So if we say psi 0 xa is c, then this psi just becomes equal to the absolute value squared, but now with a square root to the determinant of the metric over n. Right? This square root of the metric comes from the Hutchin star. So this is a generalization of what we've seen before, when we just integrate in the trivial metric. We just dx here, the metric is trivial, and this would be just a real line. So, but this is the generalization for this non-linguistic models. Okay, we also know that the odd degree forms correspond to fermionic states because they have an odd number of fermions in the United States, and the even degree forms correspond to the bosonic states because they have an even fermion. Okay, so why is this useful? Why is this language useful? Well, it turns out that the supercharges also take very nice form in this language. We have the supercharges here. Supercharges here. Yes.
Like it why is it useful for us to write shooting and
Say it again.
why is it useful for us to write
To the
Hamiltonian?
well, this is not the, this is the Hilbert space. So,
Oh, they have created this piece. Okay. Why is it useful for us?
so we're going to see that. So for now, it's just a bit of a formal countstation that works, right? So we can just do this. Whether we call it psi dagger of A acting on 0 or we call it a 1 form, it's really a bit of a formal translation, but they have the same properties. So the dimensions of these spaces are equal. They have the right anti-symmetry properties, and that's just the observation so far. And we can just represent. We could keep working with this formulation and never worry about it. Never worry about anything else. But it's just a sort of a useful translation to write it in this form, because we can make contact with these standard differential geometric. It's just a one-to-one translation between the two, perhaps a bit formal, but it's useful as we'll also see. Yeah.
Why is there is alpha bar? Why is that
So these objects are, they sit in, these are ultimately wave functions, but they're states in the Hilbert space corresponding to some complex value wave function. But ultimately we need this inner product of the statements. We need the norm to be positive, right? And in fact, it has to equal for normalized state. The norm has to be equal to 1. The only way to do that with complex valued wave functions is to do a complex conjugation. Just like usual, the bra, the state corresponds to complex conjugation together. Yeah, we need the norm to be positive. Okay, so yeah, so let's see what Q and Q dagger correspond to in this differential form language. So upon quantization, we replace these x dots by the momentum operator, and the momentum operator is just given by, as usual, by a derivative with respect to x. I haven't, I don't have it here anymore, but we just, this commutation relation tells us that B is like minus I dx. And this is just, as usual, a derivative. So if we plug that in here, and also plug in psi dagger, then we see we get the following expression. So we get that Q is like, so it's literally dxa. It's a multiplication with the one from dxa, which is psi dagger A here, wedged with a derivative. Sorry, it wedged. And these indices have to be summed over, so I'm contracting with the metric. But this guy, this is nothing but the exterior, the definition of the exterior derivative, right? Exterior derivative acting on the differential form takes the derivative and maps the differential form to a B form to a B plus 1 form. Okay. Now we can do something similar to dagger. So it turns out that the dagger, perhaps unsurprisingly, will be thought of as the it's the conjugates, the conjugate in the inner product of the exterior derivative, which is denoted by the dagger, but can be expressed in terms of d in the following way. It's n plus minus 1 star and star. Okay, and this guy you can check. It maps p forms to p minus 1 forms. Okay. So how to derive this expression for the dagger is to define it in the following way. So you say that alpha and beta is equal to dagger alpha and beta. And then plug in both sides with the product here. That's how it is beta. And then plug in both sides with the product here. That's how you see the touch stars. Okay? Okay. So this is speaking of the quantization of this symmetric sigma model in a differential form language, where now the supersymmetry transformations can be thought about as maps between p-forms, either mapping it from a p-form to a p plus 1 form, or from a p-form to a p minus 1 form. And that's also exactly going from a boson to a fermion, or fermion, because it changes the odd, changes odd forms to even forms, and even forms to odd forms. Right? So that all matches with our expectations. Now, we also have that the anti-commutators of Q and Q is equal to 2H. In the differential form language, we therefore find that H is equal to a half delta, where delta is just an expression in terms of these exterior derivatives and its conjugate. And this is nothing but the Laplacian on a curved manifold written in this differential form language. Okay. So this guy in particular, it acts on the function in the usual way that the Laplacian acts. So now I didn't write it down, so I'm going to have probably make a mistake, but it's something like G and then in addition derivative, something like this. So if you just work out the definitions of D and dagger acting on a function, you reproduce this guy. You see, this is a very sort of clean and short way of writing in the definition form. Okay, and what do we have? Well, just like in the supersymmetry case, we can consider the expectation value of the Hamiltonian, right? We sandwich the Hamiltonian between two states. In this case, our inner product is some P form is given as follows. Right? It's implying using this definition of inner product here. And we can write this in the following ways. We can write this as just plugging in the expression for delta, it becomes d dagger of omega plus omega d dagger e of omega. Now we use the fact that d is the conjugate of d dagger, and take this d to the other side if we put a dagger on top of it. Plus d omega given the dagger. And these are just the norms. These guys are the norms of these differential forms. So in particular, the sum of two norms is greater or equal than 0, and only saturates 0 when both these guys are 0. So this is so we have that the expectation value is delta is equal to 0 if and only if d omega is dagger is equal to 0. So, well, we recall that the zero energy states in our theory correspond to these guys. The differential form language, they correspond to differential forms which obey these two equations. And these two equations are known by a P form that satisfies these two equations. These are known as harmonic forms. Okay. I realize that perhaps if you haven't seen that much differential geometry, this might be a bit tricky to follow. Yeah, any questions? So maybe we should take a break and take questions to see if we can elucidate any of this. So I just want to keep in mind that ultimately, in could work in our previous language. It's just convenient to repackage these fermion operators as these forms, differential forms, because we get this connection between supersymmetric Hamiltonians and very natural objects in terms of the geometry of the target space. That's the idea. Okay. So the statement here is that the translation is therefore that supersymmetric ground states which are mean those zero energy eigenstates, which are annihilated by both Q and Q dagger, they are in correspondence with these harmonic forms. Harmonic forms on M. Okay. Now, let's denote by that's denoted by well, that's decompose all the harmonic forms on a manifold M in terms of this degree P, in terms of the harmonic P forms. If you think about these spaces as vector spaces, the basis built up by all the harmonic forms on this manifold, then you can construct a topological invariant out of the dimensions of these spaces, which is known as the Euler characteristic. The Euler characteristic of the manifold M is a topological invariant that we can express if we say the dimension of harmonic forms on M is the number BP, which is also known as the Betti number, and this topological invariant, the Euler characteristic, can be expressed in this way. It's -1 P times BP. Okay, so that's invariant under deformations of the metric of the space, as long as the topology is the same. But this, in our translation, this is nothing but the phrase in -1 P. Right? Because we've identified the harmonic forms of supersymmetric ground states. Now, here we see that for odd forms, odd degree forms, we take into account the minus sign, which is precisely the fermion, which corresponds to the fermion number of the supersymmetric ground state. And otherwise, this guy is H 0. So this guy, the differential form language is nothing but this. Is that clear? Okay, so the statement that the Litton index of the supersymmetric sigma model is invariant under all these deformations, it doesn't depend on the parameters of the theory. The differential form language becomes the statement that that this specific combination of the dimensions of these spaces computes a topological invariant. In other words, you can identify the couplings on the right-hand side of this supersymmetric sigma model as metric deformations of this manifold. Okay, so that's perhaps.
Sorry, would you mind just repeating the last?
Yeah. So remember that when I was writing down the sigma model action, it's not very.
Yeah.
When I wrote it down, there's very the couplings that appear in the theory are geometric couplings, right? So
Yeah.
the GAV of X multiplied the GAV of X multiplied the kinetic term of X's gamma A and C was in the David-Chivita connections of the appearance of the Riemann tensor. So you can think of these metric dependent quantities as giving you the coupling constants, as encoding coupling constants in a sigma model. And then it's not that surprising because the topological invariance here corresponds to the independence of these couplings.
When you say sigma model, of course, here you are defining a 1D sigma model.
Yes, this is one.
So it's a word line.
It's a word line.
Okay. So, does the statement generalize to 2D sigma model?
Yeah.
I mean, on the left-hand side seems to be generalizable. Exploring other cycles of the manifolds.
Well, this explores all cycles of the manifold.
But you're drawing a line, right?
You're probing the manifold with a line.
Yeah.
But,
so probably with the surface.
but we have all types of, so we can connect the P form with this, constants where there are that are captured.
Yes, maybe my statement is okay with this. Okay, so the normal part is also extreme geometry has a few differences, like in the sense that, you know,
Yeah.
things that are and whatever are.
Yes,
the
exactly,
same.
exactly.
So that you cannot really see here.
That you can see here.
So mirror symmetry one.
Mirror symmetry function.
Yeah. So, but
So what goes
have it extended on the left, and we know that it's in the left hand side. And we also
so,
extend the right hand side.
so in some sense, this is like a classical way of viewing the geometry, but probing it with this point particle. I guess once you start these geometries with higher objects such as strings, then you know there can be even, I guess, more surprising correspondences. So it can be the case that two sigma models on different target geometries actually describe.
Just a concept wall in your program, you can see those Betty numbers being the same from there, right?
There's an isomorphism between harmonic forms and closed forms modular. Those two things are equivalent. So we can also think of these Betty numbers as the dimensions of the cohomology, the Rand cohomology.
So, the identification of this Euler characteristic as a between index, is it heuristic or is it mathematical?
So, no, it's not heuristic. So we have made a translation from our quantum mechanical system to a differential formula. And within this translation, the written index corresponds to this Euler characteristic.
That's what I'm asking. Is it heuristic or is it mathematical?
No, this is mathematical. Yeah, this is- we just use, we can describe it. Maybe I haven't presented it in those figures. More.
I know just at the last statement.
Yes, the last statement is correct. So this is correct. Well, I mean, I should say that this is not just any Hilbert space, but this is the Hilbert space associated with the supersymmetric sigma that we define. But if you think this model, this statement is true. Now we can look at other supersymmetric quantum systems, and then, you know, depending on whether they have a geometric interpretation or not, well, we can only write like geometric objects on this side if there's some geometrical interpretation on this side. So for the previous class of Hamiltonians, the geometric interpretation was a bit trivial because we just considered the real band. The previous class of Hamiltonians, the geometric interpretation was a bit trivial because we just considered the real band for Rn. So we didn't make it explicit, but even in those cases, you can write this equation. But this then, I guess this would be just the other characteristic of Rn, which is very trivial.
Generally, I would say we think that's strong operator, Dirac operator. So this chi of m being the index of something, it's often the case. It's not just it's generalized.
So we've looked at a specific model, but there are many more models with nice geometric interpretations. You can get natural geometric, you can compute other geometric objects, the topological invariants, but not necessarily the Euler characteristics. There's a whole variety of these guys, and they will correspond to supersymmetric ground states of some specific fundamental system.
Is this the only topological invariant in this series, this Kalia?
No, I don't states. Is that true? Because you have to take a specific dimension of it.
It's coming cycle this type since the during.
And these cycles, they could shrink, I guess. But you can introduce some cycles upon metric definitions. I would actually say that, our quantum mechanical intuition actually implies that they are not topological invariants, that numbers, because we know that the precise number of ground states can change the definitions of the theory. It's only the difference that remains. So I think I can answer this question not as a mathematician, but as a physicist, as a no, as a convincing no. That's sort of the nice thing about this translation, not as a mathematician, but as a physicist, as a no, as a convincing no. That's sort of the nice thing about this translation. Somehow, supersymmetric quantum mechanics gives a very nice framework to understand these differential geometric type of things. But we're not there yet. We're coming to the main state.
Okay, if you open a mathematics book, you definitely say that the numbers are invariant. So you're probably including some operation that is somehow some number, right? Yeah, I think so.
Yeah.
So, I mean, the operation of pitching
Maybe that's
is technically not allowed from a mathematical perspective. And I guess that's what you do, you're pinching something.
Can we Google that?
Okay.
So, sir, this product characterization is it different for different models of the country? Is the same for different models? Because of now we're getting sigma model, right?
Yes.
So now if you choose another one,
Yes.
so would you getting the same answer or exactly?
No. Generally it will be something else. So here we have a correspondence between harmonic forms and supersymmetric ground states. And then we see that the width index is precisely what mathematicians would call the Euler characteristic. But if the supersymmetric ground states correspond to some other objects associated to the manifold, then the alternating sum of their dimensions would be the answer. So yeah, I don't now have an answer, but it's not only the Euler characteristic that appears in this more general framework relating quantum mechanics and differential or geometry.
So in a sense, we've like fine-tuned the interactions and the couplings that we're considering in this supersymmetric sigma model such that this.
That's right. So
such that we get this correspondence.
Yeah. So when I wrote down the sigma model of action, no, it's very constrained because the metric that appears in the kinetic term of the bosons has to be the Riemann tensor associated with that metric that multiplies this Fermi direction.
Right. And we've got that fourth term.
Yeah, that one is the one. Yeah, that one is the one I mean. So
Right.
yeah. Right. So that could have been anything, right? But it has to, for supersymmetry, it has to be associated with the Riemann tensor of that metric that appears in front of the scalars. But generally, why should that have to be the case?
Are there other supersymmetric terms, like natural terms that deserve some supersymmetry and even?
So in this specific model, yeah. So
because I imagine maybe you could do that and it still has some supersymmetry, but lose some.
yeah. To properly answer your question, I think you can put also this potential that we've been seeing previously, so this h of x. You can also introduce that in this case. And then you also get a connection with a well-known field in mathematics code more spherical. So you can consider functions on these manifolds and still preserve supersymmetry. Okay, but yeah, so as I said, we have much time.
Well, technically a bit over, if you take a couple of minutes.
Yeah, it's like 95 minutes. Yeah, so we only worked, we've only made this translation in the operator formulas, but we also have the pathing. I don't have the supersymmetry transformations anymore, but we know from these very general arguments that supersymmetric pathing growth localizes the system. It localizes on the zero locus of these supersymmetry transformations. Right? That's what we discussed extensively the last time. I don't have a supersymmetry transformation anymore, but quite similarly to the previous case, we just localize onto zero nodes. So remember that there was an x dot appearing in one of these transformations. So x dot has to equal to 0. Also, the fermions have to equal to 0. So this if you put these guys together, then we satisfy this. So the claims that we have localizes on these configurations and the quadratic fluctuations around this. And we can express that as in the second computation we saw yesterday. We can express the path of the growth. So the path of the growth, we can express it in this way. So the functional integral reduces to an ordinary integral over zero nodes coordinates. Over zero nodes coordinates. And similarly, okay. And the action evaluated on these zero nodes is nothing. So the kinetic terms disappear. Because we're only looking at zero nodes, we only have this term, this fourth fermion term that is that. So the fermions themselves are replaced by the zeros. Okay. Okay, so this is the remainder of the path integral. Now, what you can first of all see is that because there are four fermions here, for odd n, we'll never be able to saturate the Grassmann integration. This integral will always give 0 if the dimension n is odd. And that's a known property of the Euler characteristic of a manifold. So the Euler characteristic for odd dimension manifolds is equal to 0. So that's good. Now, okay, let's work this out in the case that we work with two-dimensional Riemannian manifolds, so Riemann surfaces. In that case, the integrals for n is 2 that's following u2x still this exponent. Now, yeah. in 2 dimensions, so we work with a 2-dimensional target space, the Riemann tensor can just be expressed in terms of the metric. Turns out that in 2 dimensions, the Riemann tensor becomes the Ricci scalar. Minus the product. Now, express the Riemann tensor. Minus 4. So that's a special property with dimensions. We can do that. And then there's still some fermions multiplying this. Okay, now we use the Grassmann-like nature of these variables to extend the exponential and only keep the term that contains these 4 fermions. Because that's the only non-vanishing term. And if you work that out, so what you see here, because these guys are anti-symmetrizing this index part, because the fermions are anti-commuting, this can actually be expressed in the following term. So it becomes get 1 over 4 pi d to x. We integrate out those fermions, d to x 0, and then there's the square root g in the Ricci scale. Okay. So this is what the path integral reduces to. Ricci scale is a function. It's coordinates. This is what the path integral reduces to for the supersymmetric sigma model in 2 dimensions. But this is quite a different expression, of course, than this summation over the dimension of harmonic forms. But this is a known statement in mathematics. So it is known that the Euler characteristic can be computed by an integral of the Ricci scale, which is known as the Gauss-Bonnet theorem. Okay, but here we see that sort of the connection, the equivalence between the Hamiltonian and Lagrangian formulation of quantum mechanics sort of predicts this mathematical theory. So it's quite a nice reformulation of an important mathematical result. It sort of follows naturally from this. Okay, so I think that's what it was. Good break. I can take a bit shorter for the next, for the last lecture.
Okay, then let's take a 20-minute break. So, yeah, I think we should be coffee.
Well, just by response, we decided that the harmonic forms, to which at least it is, we translate this back to physics. These are the wave functions that are annihilated above Q today, which are zero energy, ground states. And when it's a pot, when it's a fermion, that particular person wants an opt to the differential. And an opt to the differential. So P form, where P is an opt. And then it's also computing. And that's exactly what we're computing here. So it's because of this translation between the harmonic forms of the parent space.
So these are like partition functions, and partition functions contains all the information about your system, about your system, right? And these are the variables. Yes. Variable can be variable, yes. That is this one, right? But this does not contain all the information about the. But I can't see why. These are very similar. So where is the information going? So for example, here we just inserted a minus.
Yes.
So why is it creating information?
Well, in principle, this way of writing, I agree that in this way of writing, it seems to suggest that you know what the Hilbert space is. Right? And if you know what the Hilbert space is, then you can complete this one, or this it doesn't really matter. But the notation is a bit, yes, wrong suggested, because you know that you don't complete this guy, you don't. You only need to know zero in these states, because everything else cancels. But because
For example, let's say I'm working with the that's how the data is there. Yeah.
so you know that this guy, we need to diagonalize the and find all the eigenvalues and the basis. Here we don't need to do that because notation suggests that we don't have to, because we know that the only distance that we can contribute in the surface of the theory, that's crucial. The theory has to, the Hamiltonian has to be of this form. But if the Hamiltonian is of this form, we know that we only need to know what the zero conjugate.
Can I see some of the time in the
Yeah, because any other state will be there. So if we have some state inside, then there's an associated, so there's some bosonic state outside. There will be some permeable state. That is related to this one by Q or Q dagger. Yeah. Don't remember the convention number. Yeah. And Q commutes with the Hamiltonian. So the only difference in at least in the sense of the eigenvalue, in the sense of the addition functions, the only difference between these guys is that one goes in one is they have the same.
F will be 0 for this one, F will be 1.
So they cancel because they have the same eigenvalue of H.
And then how to see this from like why is just the difference?
Well, I mean that we did yesterday. So one way to see is the localization principle. So the localization principle tells us that we don't have to do full functional integral. We only have to do this integral of the solution since BDS equation. The zero values of the BDS equations. That typically reduces this function to some finite dimensional coordinate. So also here, we're seeing much less. We actually don't need to integrate over all the modes, we just integrating on the zeros. And so that, and also the action simplifies significantly on the zeros. Because all the kinetic terms disappear, right? Because the zero node is just a constant, it's a constant function. It doesn't have that many. Yes, in some sense it is, because we've been saying forget about all the high energy states. In fact, forget about all the energy eigenstates except for the one that is zero. Zero. So in some sense, this is like a low energy, very, very low energy.
So this is my question, like, was maybe when you calculate this, so can I take this in terms of critical exponents? You know, if this kind of thing, like, they have critical exponents for different type of models, is that different schemes?
Yes.
Check out. Can I move from this? Whatever.
Yeah, but I mean, so this captures something about. Yeah, but I mean, so this captures something about namely the difference between fermion and boson ground states. Because what is one is something that tells you something about how correlation scales.
I think the statement we trying to make is that the order is variant in the velocity function, right? And critical exponents, they remain unchanged by the scaling of scale, right? So is there a connection between
Yeah, so this is a much stronger variant. So critical exponent.
yeah, because critical exponents are only valid for scaling, and this is what people call it.
This is basically any definition, but at least you have to preserve the topology.
So Sam, is this still an approximation, especially in the language of forms? Because in the language of forms, you can only create so many states, right? You limit so you have some kind of a natural truncation, because your states down there, you can only have so many wedges. So this actually provides a natural way of capping how many states or what type of states you can use. So can you still call this an approximation, or are you fully calculating?
No, it's exact. It is also exact.
So the language of differential forms actually makes this more clear, because you could only make so many states.
Yeah.
Limited.
Yes, exactly.
Okay. So then the language of forms has a lot more than making connections. It's
Yeah.
Okay.
Yeah. That translation works. I mean, it's not necessary for the physical model, but it works very much. Yeah. I guess, yeah.
by the way, like still recording. Although this is a tape.
Just to mention, why are you working with now? Like suddenly we started with non-linear phenomena. Oh, okay.
It's just another class of models.
Okay, so we just want to study them.
Yes.
There's no.
Because there's a connection.
So, okay. So I thought like it was like continuous chain of thought and we were next studying them. But it's just that we want to study with index of this, so we are studying.
Yes. Let me just look at this. I guess of course it's definitely
Yeah.
So I guess it's just a finer chronological area.
I think, just trying to cost, I think what's happening is that there are more scenarios which are probably stricter than online programs. If you describe for two critical points that we have that each works functional change. So that's happening. Many of those are
Changing.
changes. Yeah. That's because you're thinking on the side, strictly as a online operation.
It has a bigger.
Yeah. So, there's no sense to do. That's not like there's some-
I think the wrong statement, which is one of the people I mentioned very much. It's not completely because of the reason from very much rather than, and then the direction came out again. Like, we give today, like, I just go to the like,
I'm not sure, man. I think you may be able to say. Okay.
but it's not.
Hmm.
So you need to
I know it's not. Yeah.
Last hour.
Yeah. Okay, yeah, so we're gonna now change pace a little bit. But maybe I should say that what I hope to have sort of demonstrated is that, well, first of all, that with supersymmetry, calculations can be performed exactly. We can compute these indices, and in addition, we can compute them in two ways. And that these two ways sometimes give a different perspective on a single object, and that can be quite powerful. And this is something that property is not limited to quantum mechanical systems. That property extends. So somehow this equivalence between the Hamiltonian and the Lagrangian formulation in QFT is quite powerful connections or gives different perspectives on these partition functions that are both useful and yeah, and sometimes very powerful. And okay, so and typically what is also true is that somehow the path integral it knows it reflects more clearly the underlying geometry of where the theory lives on. It has a more geometric flavor, whereas the Hamiltonian formulation has more of a state counting, more of a Hilbert space, more of a quantum interpretation. And sometimes there's a very nice interplay between these concepts of geometry and states. And yeah, I think that is a very general thing that appears in many dimensions. And my own research is centered in the context of four-dimensional supersymmetric theories. And so what I want to try to explain today is sort of a similar type of index that can be computed in four-dimensional theories, a Witten-like index object. And we're going to focus on the Hamiltonian formulation. And maybe if there's some time, I say something about the perspective from the Lagrangian formulation, but we're going to focus on introducing this index, also known as the superformal index, in the Hamiltonian format. Okay. I wanted to correct one statement. So I was completely wrong, of course, about the Bethe numbers. Those are topological invariants. So actually, this Euler characteristic is invariant under slightly more drastic deformations that would change the Bethe numbers. So not within topology preserving transformations, but so Euler characteristic is not sensitive. So, don't believe that. Okay. So let's start with the n equal to 1 supersymmetry algebra. What I also hope to convey is that many things in higher dimensions just require a little bit more bells and whistles, but the essential structure is similar. So we have seen in the lectures of Mario that there's this symmetry algebra in 4 dimensions or various dimensions. It's quite similar to the quantum mechanical complex. We have 2 supercharges, 2 anti-commuting symmetry generators, but now they carry an additional spinorial index associated to the Lorentz spin. And in this case, they combine into these space-time translations, which contains, of course, the Hamiltonian generator of time translations. In this case, also spatial. And similarly, also to 1 dimension is that Hamiltonian, in this case, is formal momentum, commutes with the charges. That's a very beautiful. Okay, then so the 2. So I will not be talking about supergravity. So we're not including gravity. So we're going to constrain ourselves to spin states to spin less than equal to 1. And then there are two multiplets of n equal to 1 supersymmetry algebra. We have the chiral multiplet, which consists of a complex scalar and a complex wild figma. This is now the chiral multiplet. So this is a fermion, of course, this is a boson, and these are exchanged under the supersymmetry transformation. And we also have a vector method, which contains a vector within the same order. It also contains some wild fermion in the gauge differential. This is called the vector method. If you want to write down an n equal to 1 supersymmetric Lagrangian, you can't just work with scalars or just work with fermions or just gauge multiplets. You always have to combine these the Lagrangians by making use of some number of multiples. You always have to come in this combined way. And then, of course, also the interactions and the terms that are allowed in the Lagrangian have to preserve supersymmetry. Okay? Okay, so we're typically interested in Yang-Mills theories, where these where we choose a non-abelian gauge group for the vector multiplets, and we specify some gauge group. So So to specify the Lagrangian, we need to specify a gauge group and some matter plus matter, which means chiral, which matter having chiral matter representations under the gauge symmetry. It could be the fundamental representation, like the representation of quarks in the SC3, under the SC3 plus gauge, etc. So you need to specify this, and then there are some various interactions, as I said, superpotential interactions that you can also choose. And that specifies your Lagrangian. Now, these Young-Mills theories in the UV become asymptotically free. So in the UV, we can think of them as some free Lagrangian, which in particular is conformal, so it's scaling. It's a free theory is trivially an S theory, so it's superconformal. And when we're talking about scale invariant or superconformal invariant theories, the supersymmetry algebra is enhanced. So the supersymmetry algebra, by the way, combines with the ordinary Poincaré group into the super Poincaré algebra. Similarly, when we look at the conformal group in 4 dimensions, that also combines with supersymmetry in a specific way. But it turns out that the number of supercharges then is doubled. So what structurally happens is that there, for each of the supercharges here, so for each Q alpha, I get a partner, which is also known as the superconformal charge, S alpha, which is by the commutator of a special conformal, so it's a special conformal transformation. So if you write down the index structure, it's something like this. We take the commutator of a special conformal transformation with one of the supercharges, and this gives something proportional to this real supercharge. Okay. Okay, so in Euclidean signature, these S alphas, Euclidean signature, are thought of as the dagger. The dagger of our supercharged cube. So maybe you see where this is going. You want to have a pair of supercharges, a Q and Q dagger, that satisfies such that we get these positive interconditions that were so powerful in supersymmetric quantum mechanics. So indeed, you can work out the algebra of a supercharge and its Hermitian conjugate within the superconformal algebra, and you get something like this. This is equal to delta, which I'm going to define momentarily. Right. writing down some charges here. And we have similar anti-commutator. We deal with keys. Okay.
Are you not?
Yeah, yes, well, I think let's see, I think I think that's true in Lorentzian signature. So in Euclidean signature, at least for the superconformal algebra, this sort of splits into two separate supercharges. Yeah, so connected to that, so let me explain what these guys are. So we're looking at the conformal transformations on R4. So conformal transformations on R4. So we're working here in Euclidean signature. We're gonna think of R4 in the following way. So we think of it in spherical coordinates. So we have the origin, then these concentric circles are face space. That's how we think of R4. And then, in this case, what is delta? Delta is the generator of radial translations. It's also known as the dilatation operator. So this one moves you. This one scales the sphere, for instance. It's the scaling transformation. And the m's, m and m tilde, are generators of the rotations on S3. So the rotations on S3 are given by SO4. And SO4 is SU2 times SU2. It's labeled by 1 and 2. And m tilde, they with their indices. Where both of these take two values, 1 and 2. They correspond to the generators of these SU2s. Okay, so they rotate this free space. So these wild fermions here, these representations only transform under a single SU2. Right? That's a common. And similarly for the tilde diffuse, they only transform to the second SU2. Okay, and this is so what I want to do is ultimately we're going to want to define an index. So what I'm doing here is I'm finding an Hamiltonian which can be written as a Q, as an anti-commutator of Q and Q dagger. But I also have to construct a Hilbert space. Right? So how do we construct a Hilbert space for this conformal fluid theories? Well, there's something known as the operator state correspondence. which is the statement that the local operator in R4, so let's say we have R4, and we insert the local operator here at the origin, where this operator can consist of all the elementary fields in our theory. So I can make some gauge invariant combination of the fermions, the bosons, whatnot. So create some operator in this free formulation of the theory. And the statement that is for the operator state correspondence is that in a CFT, I can restore the geometry without changing the physics. What I can do in particular is I can do a scaling transformation which makes all these S3s that are here shrink as I go towards the origin and grow as I go towards infinity. I can do a scaling, a local scaling, such that I essentially make all these S3s of the same size. Okay. So what happens then is that I map the R4, I map it to a cylinder where the slices of the cylinder correspond to these concentric circles in the thing. And the radial direction here becomes the vertical direction of the circle. It's basically stretching out or pinching in the cylinder to this mapping. What happens to a local operator with which I acted in the origin here? Well, that defines now a boundary condition at t. So I'm going to call this direction the time. This was the radial direction here. I'm going to call it the Euclidean time direction here. So this local operator at the origin defines a boundary condition at the infinite past of the cylinder, and that's nothing but a state. So boundary condition on a spatial slice defines a state in the Hilbert space. So this is what is this. So that's where the name comes from. The operator state correspondence. It's a general statement for conformal field theories relates the spectrum of local operators to the two states of the Hilbert space fields. Okay. So we can. So that means there's a one-to-one correspondence between all the operators that I can construct from the basic fields in my Lagrangian and the states of the Hilbert space. Okay, so now we have the ingredients to define our index. I'm not gonna fully define it, but we're gonna do it slowly. So I call it I again. I'm going to define it as the trace over this Hilbert space. I mean, the in principle, of course, means a more abstract construction of the Hilbert space, but for us, we're going to work with, we're always going to have in mind that we have some free gauge theory description, and then we can think of the Hilbert space as constructed in this specific data. I think that's a useful thing to have in mind. We're going to put a -1 to the f, of course. We're going to leave this part open for a bit. So, in addition, we're going to put in the Hamiltonian. We're really going to define an index here, where I'm going to not call it h, but I'm going to call it delta. And delta is exactly this anti-commutator of Q alpha. Also, I'm going to be even a bit more specific. I'm going to say this is delta is the anti-commutator of some Q, double Q, where this Q choose it to be any of these supercharges that we have, but we're just going to be defining it as a cube with the minus, with alpha, is alpha equal to minus. Yeah, they take two values, they're currently denoted by minus and plus. Okay, that's just the dimension. Okay, so, well, so this is defining this in a specific way gives us all the properties that we've also seen in supersymmetric quantum mechanics. So we first list those. So first of all, we have that this delta is kind of Hamiltonian, commutes with Q. And Q dagger. This is furthermore, in any its expectation value in any state and because it's the anti-commutator of the Q and the Q vector, we can, as usual, write this as the sum of two norms. Shows that it's larger or equal to zero. I think that is larger or equal to zero. And in addition, if this is saturated, it's zero if and only if Q acting on psi equals dagger acting on psi equals zero. Right? Now, for all the arguments that we had, in particular because this being produced with the Hamiltonian, we have that all the states with non-zero eigenvalue of delta are paired, and they will cancel from the trace because we include a minus sign for the Fermion counterpart of the other. So just as in supersymmetric quantum mechanics, our index will only get contributions from states that are not partnered, that are annihilated by this Q. Trace, we only have to use a trace of the subspace of states that have delta equal to zero because of the minus insertion. Okay, so far so good. Now, somewhat more precisely, it is because this is not quite the Hamiltonian, right? Delta is not quite the Hamiltonian, but we can read off what it is by plugging in this anti-commutator and taking alpha and beta equal to minus. And what you find, what happens is that delta is given by this delta times 2J1 plus 3 over 2 power, where J1 is the Cartan generator of SU21. So it's the projection on the z-axis, if you will, SU2 spin associated to the STU to one rotation group. And I didn't say it yet, but this R is the generator of the R symmetry. R symmetry is a symmetry that acts under which the supercharges rotate into each other. In this case, for the U1 R charges, they just get a phase. And it's part of this homology. Yeah, so in this case, because delta is not quite the Hamiltonian, but it's this combination of quantum numbers who are not really looking at, so the states that contribute to this trace are not just the simplest vacuum zero energy. Well, maybe that's semantic, but nobody would say that's part of the superconfirmation. So it has some commutators with, I guess you can view it as an other automorphism. But you can also, yeah, I think that's a fancy way of saying that, but there's just some element, there's just a set of commutators, and the R symmetry is part of this. So in this case, so it's not just supersymmetric ground states, but as you can see, as long as the scaling dimension of an operator in combination with its spin and R charge gives 0, these states will contribute to the index. These are also these are known as Carter, not generally known as BPS states. BPS states are states which are annihilated by some supercharge, maybe not all supercharges. So in this case, we have selected specific supercharge within the superconformal algebra, and they only have to be invariant under this charge. Then these guys are the only ones that will contribute to this index. So this is not a unique index. There are multiple indices that you can define, and they will be slightly different in nature. But okay. Any questions about that? Yeah. So. Well, because we're not working with a somewhat bigger algebra, there are more operators in the algebra that commute with Q, right? So the whole argument that tells us that the index localizes onto these delta zero states is not spoiled if we add some additional operators here, as long as the supercharge commutes with them. Because the argument that works for delta works also for these other operators. So it turns out that we can construct two other operators that are simultaneously diagonalizable and commute with Q. So these are given by the curiosity here, which is usually called P. This guy is J1 minus 2 R. That's J2. You can add a Q. Minus 2, and we still have our why is this? Why do these specific combinations commute with the supercharge? Well, this choice of supercharge that we made. this choice of supercharged is minus. This guy has quantum numbers delta or one half, relates bosons and fermions, and then it shows it with this minus sign here, which means that this J1 eigenvalue minus one half, and it's R's charge. It's conventionally chosen minus one. That's convention. Then you can just, and it doesn't have dotted indices. It doesn't have the dotted indices. So that means that J1 minus one half R minus one half is R charge. That is zero. That charge is zero. So it communes with this guy. It's not charged with SU2. So we can also, it's just as charge 0 under this J2. And that's why we can add these two operators inside the trace without spoiling the arguments that tell us that this index localizes onto the delta equal to 0 subspace. Okay, so we see that in this case we have a somewhat richer object. So in quantum mechanics, we just have a number. In this case, we get, because the supersymmetry algebra is larger, we get an object that actually can depend on two complex variables in the Q. In fact, if the theory has global symmetries are symmetries that commute with the super Poincare algebra. Well, so they commute with the supercharges, and you add additional fugacities that are coupled to these global symmetry charges. This can become have an even richer dependence. Okay. So the idea here now is that what does this thing do? Well, ultimately, it's a trace over a Hilbert space. So ultimately, you can write it as some sum over n comma n, let's say, where you have some integer numbers have some powers of p and q. So in other words, instead of a single integer, we get a whole list of integers that divide our delta into zero space. So we divide our delta into zero space into subspaces which have some fixed eigenvalue under the exponent of this p and q. So it gives a more refined counting than just, it's not just the difference of bosonic delta equal to zero states minus fermionic delta equal to zero states, but we define it by being able to fix these eigenvalues under J1, this combination J1 minus the half plus 2. Okay? But otherwise, the object is very similar. Okay. And so that is what is the superconformal index. But it might be a bit abstract. So to end today's lecture, I thought to give a slightly more explicit example of how it looks for a concrete simple field.
Just clarify, so for the previous case, the index you were calculating was involved under virus transformations. So the deformations here are situations where the guess states meet and become, long and then get removed from the guess spectrum or something.
Right. Let's see.
Like I was talking about wall stability, or if that's not a discussion.
Well, first of all, it's very independent of data. But then, of course, the
Beta is
data here is some continuous parameter. It's like the temperature. Yes, it's invariant with that. But more generally, I mean, I guess this delta contains the its eigenvalue or the conformal dimensions of all the fields. And so as you change couplings in the theory or whatever, while preserving supersymmetry, generally these conformal dimensions will change. Right? But the index isn't there. So the index is insensitive to this eigenvalue product.
Yeah, okay, so that's the same that if you do marginal formations of a superhomo theory,
Yeah,
the index does not
index doesn't change.
change. But it's the number of VPSAs could change or not.
So in principle, yes, it's the same story there. So because this is, I use the letter D, but maybe I should be, it's not really a degeneracy, but it takes the number of bosonic states for some fixed quantum numbers in an M, quantum numbers in an M reduced operators, but it subtracts E of reduced operators, but it subtracts E of form. So it could be, again, that some states live on the spectrum as you deform the theory. So that in particular, their conformal dimensions might not satisfy this, the fact that this has to be preserved. Right? They might not satisfy it, but they have to live through theirs. And so the index is insensitive to that change.
But isn't that what we normally call crossing a wall with stability? Because I mean, the only way for VPS state to lift is to become long.
Right.
Two of them,
Yeah.
say, have to combine,
Yeah.
become a long, and then okay.
But the index is insensitive to such combinations.
Two of them,
Yeah.
say, have to combine,
Yeah.
become a long, and then okay.
But the index is insensitive to such combinations. Yeah, yeah, yeah. So I think I still have about 5 to 10 minutes. Okay, let's see how we can compute this index in a simple example of just a single free Caron single free Caron. Okay. So the Caron the theory of the Caron has a complex scalar, as we said. There's a while fermion. And then we add the CP conjugates. So we have we need to impute the complex conjugate. Well, that. And then finally, there are various derivatives. There are 4 derivatives. So what we're going to do, sorry, I should maybe be clear about this. What we're going to do is we're going to construct the Hilbert space and perform the trace. Right? And constructing the Hilbert space, we do it through this operator state correspondence. So we're going to write down all the fields that we have in our theory, and then construct all possible operators out of them, and then construct the Hilbert space associated to these local operators, and then evaluate the index. That's the aim here. The derivatives, I'm giving a spin on the fish. Write them here, d alpha dot, as opposed to usual d. Plus minus dot, finally, minus dot. So these are what are called the single letters. And I can construct operators out of these guys and all their derivatives. And by multiplying the single letter operators. We want to know what their dimensions are to compute the index, to know what the powers of P and Q will be. And also to know which of these guys are BTS operators, and which of the guys satisfy the condition that their delta is equal to 0. this can just be computed very specifically, just listing all these quantum numbers. So the conformal dimension, or the scaling dimension of the scalar is, of course, just 1, and it spins 0. And then the R charge is taken as 2/3. And if we add this together, so if we look at the delta, which is big, small delta, which is big delta minus 2J1 plus 2 R, you can verify that this delta is equal to 2. This means that it's an operator that is not annihilated by Q, because it doesn't have 0 eigenvalue with a small delta, and that means that this will not be seen in the index. Right? This will cancel. So you don't have to pay attention to this. Now you can do this. You can do this. Listing of charges and check which of the operators have delta to 0. So for lack of time, I'm not going to fill out this entire table, but you can find it in one of the references. Reference structures on got it. Just going to combine. Okay, and it turns out that the BPS operators, so the operators that have the right charge combinations, is this psi plus. So that I'll write the dimensions. So this is 3 seconds. Plus means it has eigenvalue half of J1 instead of J2. This is minus 1/3, and then you can find that this is equal to 0. The other operator which has delta equal to 0 is phi bar. Phi bar is 1, 0, 0 minus the first. Also get delta equal to 0. And then two of these derivatives also have the right quantum numbers. So the scaling dimensions of derivatives are 1, 1, 1, and 1. Right? And then the plus and the plus dot indicate their values, eigenvalues of the J1 and J2. So this will be plus 1/2, etc. And it turns out that this guy has the right quantum numbers, and then the third one. So, okay? All right. So now that we've listed these quantum numbers, we can proceed to compute the index. So, okay. So we can construct, so what's called the single letter operators that we can construct are the following. So single letters that are following, we can take our psi plus, which has delta equal to 0, operators of type 1 are psi plus. And then we can act with an arbitrary number of these two derivatives. So that's d plus dot to some power n, and d plus minus the some power n. This is what's called a single letter operator because it only involves a single field. And the second class of operators that satisfy the delta equal to 0 condition is the same derivatives for any integer n and m. But now acting on phi. Okay, so let's first compute the index. Let's first compute the index associated to the subspaces of Hilbert space, or which restrict the Hilbert space to only contain a single element. So we're going to trace over this set of somebody goes set. Okay, let me call this O1. We have a -1 to the X. That's subdividing the Hilbert space and looking only at this subspace generated by these operators. At the -1 to the X, so we have our P to the J1 minus I have R plus J2, and we have Q to the J1 minus minus J2. We know that delta is 0, so we don't have to write down that last term. So, okay, well, let's look at the first term where n and m are equal to 0, and we just have psi plus. So psi plus has J1 eigenvalue, plus has J1 eigenvalue of a half. Its R value is -1/3, so this becomes +1/6. So we have 1/2 plus 1/6 is 2/3. And its J2 eigenvalue is 0. So the P, the power 2/3. Right? And Q is the same because its J2 value is 0. Right? So it's insensitive to its J2. So we can do this. So the first operator in this series contributes a PQ to 2/3 to the index. Is that clear?
And F to -1 to the F.
Oops, there should be a minus sign, of course, because we have a fermionic operator. So it's minus PQ to 2/3. Now, the value of this D plus dot can be evaluated as follows. So in this case, R is equal to 0. And for D plus dot, J1 is equal to J2 plus a half. So this guy is not there, and there's only a P to the power of 1. Right? So if n is equal to 1, m is equal to 0, we still get this contribution. But now, so this is for the first step, but now in addition, we have plus P. Right? That's for the second operator. So now I've included both n and m equal to 0, but also n equal to 1 and equal to 0, which gives this contribution. Okay, well, you can do this repetitively. So this guy has index q. That's a q instead. This P. What you'll find is that you get two geometric series here. So the index of this full set of operators can be resummed in this way. So this captures all these, this captures the trace over all these operators that contribute to the index. Okay? So a very similar computation can be done for the second class of operators. So in this case, there won't be a -1 to the F. For the m equal to 0 case, we get instead q to the 1/3 as opposed to 2/3. And we again just get a geometric series from the derivatives. Okay. So now we've computed the indices associated with the single level parts of the index. How do we go to arbitrary operators? In particular, any number of multiplications of these guys. Okay, so that's the final. Any questions about this? is that if we have a bosonic operator, so we take one of the operators of the second kind, O2, let's say it contributes to the index of some x, right, where x is one of the terms in this series, then if we want to have an arbitrary amount of such operators, then we replace x by 1 over 1 minus x. Right? We allow there, because this allows there to be one operator, sorry, 0 operators at this time, 1 operator, 2 operators, etc. And for any of the fermionic operators, for 1, suppose x given by some y, we can have a maximum of 1 of those operators, because 2 kill each other. So we can have the option 1 plus y. That's 1 into 0 insertions for 1 insertion. Okay. So, well, this replacement, we're going to do this replacement for every term and multiply them all together. That gives all the combinations. And what you'll find is that the total index can be expressed in the following. So the total index can now be written in the following. Where all the bosonic operators are here, so we have our EQ to the 1/3. These appear in the denominator. EQ to the 1/3 times an arbitrary derivatives. And on the top floor, we have 0 of our fermionic operators, or 1, which gives 1 minus, and the minus is the minus the plus, that's 1 minus PQ to the 2/3, and then also P to the n, Q to the n. Okay. So what we've done here is we replaced each single letter operator for a fixed number of derivatives according to this prescription, and then we multiply everything together to capture all combinations of these operators. And then this should be the full index. It's a bit quick, I'm sorry for that. If you have any questions, we talk about but I guess the main thing that is connected to the last lectures and conclude this lecture is that this turns out to be a very special function, which is known as the elliptic gamma function. Some function P and Q. Okay. And this function has very remarkable properties. And those properties can be studied mathematically. But actually, you can understand the properties by looking at the path integral formulation of the same index. And that's like an appetizer to think about that. But that is what I'm working on, and you're welcome to ask more questions. Okay, that's actually all I have.
Thanks, Sam. What's the aim of this test? It's an equals 1 theory, but non-complex theory.
So this was just a free chiral multiple. So we just have a complex scale, and it's and a wild theory.
Oh, so it's a free theory.
It's a free theory.
Okay, so in this theory, you could also presumably calculate not the index, but the partition.
Yes, you can. Yes.
And then
the partition function through the path integral.
Yeah.
That can say a little bit more. So So that path integral localizes, as usual, it localizes on certain field configurations that that make certain properties of this function manifest in a geometric sense. So it is a very important. So it explains certain properties that this function has. The path.
Okay, but I think the question is, because we discussed earlier that the index should be invariant if you change couplings.
Yes.
But here there are no couplings. So if we turn on some couplings, we expect the index to be the same.
Yes.
As long as you preserve an equal should correspond.
Exactly.
But the partition function is going to become something horrible when you will not be able to calculate presumably or count, even for the BPS sector, you'll be able to count.
Well, I mean,
BPS states.
well, the thing you use is the thing you use to compute there again is this localization principle.
But this is n equals 1, right? Or n equals 1 localization. Is it powerful enough to tell you about all the
I just need one of these supercharges. Yeah. So just as this argument here for the index computation, it just requires a supercharge, a complex supercharge, which squares it to some Bosonic operator. Then I can always construct a grid index of that is protected so that only captures these delta equal to 0 states. And that is also reflected in the path integral stuff. But you might have to show that the partition function is invariant for some deformation, and then we use that deformation to go to the free limit of the theory. And the independence gives you that the resulting path integral still computes that your original theory. So you have to do something like that to compute.
Yeah, but I mean, I guess what I'm asking is if you could compute the partition function,
Yeah.
then why would you care about the index? I mean, the index is a very small, very tiny kind of subset of the partition function, right? Which is
Oh,
nice.
sorry, I'm talking about the supersymmetric partition function. So they're equivalent. Right? No, I'm never talking about a terminal partition. So the path integral doesn't receive the path integral, the supersymmetric path integral has the same information
As this, okay, because you're still only counting BPS.
you're in the path integral language, indeed, you're not integrated on the full function space. It's just a subset. It ultimately has the same information about the way you arrive at the formula.
Okay, then let's thank Sam for this wonderful speech. And that brings us to the end of today, and hopefully most of you also tomorrow for the final relative lecture. I just want to close this. Thanks.
I don't think